Nowadays, generative language models are able to generate outputs that are not novel outputs, that are not explicitly stored in their training data. And there is an important question how to evaluate the generative models, which is not straightforward. Most of the current benchmarks are evaluating generative language models by accuracy or other task-related metrics. But sometimes it can be also important to evaluate the recall. We might want to know whether a model can generate all correct outputs or not. There is two challenges to evaluate generative models by recall. First of all, the bottleneck is the lack of complete sets of correct outputs. And the second is the existence of many distinct but similar outputs. For example, if we want to generate all possible prompts that will force a language model to generate unsafe outputs, there can be multiple prompts that will have the same meaning but are formed differently. And we come to the idea of equivalence classes. In that case, there might be, for this example, two sentences that have the same meaning. They will be in the same equivalence class. So how should be an ideal evaluation benchmark for generative models? It might ignore multiple generations from the same equivalence class. That is in order to generate from multiple distinct classes in order to have diverse generations. And we have chosen a domain for which we can measure the generation's quality by recall. It is the domain of small molecules. Suppose we have a complete set of molecules which meet some conditions. For example, there are drug-like molecules in that set. We can divide the set into equivalence classes. In each class represents a single molecule, and a molecule can have multiple representations. So in each class there is a single molecule with its multiple representations. And how molecules can be represented for language models? Molecules can be converted into string representations, and one molecule can have multiple string representations. So in each class there can be multiple string representations for a single molecule. There is an important task in that field. One might have a small count of, for example, drug-like molecules, and might want to generate other molecules with the same nice properties. In that case, we can use recall to evaluate how the model can generate all drug-like molecules. What is the precision in recall for generations? In case of generations, true positives are the molecules which are generated and are in the set of from our desirable subset. And unique true positives are the molecules which are in the subset which we want to cover, but are unique. And the precision is the true positives divided by the number of generated molecules. And recall is the unique true positive counts divided by the number of molecules in the desirable subset. What we have done, we have a set of molecules which meet some conditions. We divide it by two equivalence classes. We have a small part of that set, and we want to train a model on that small part and cover the other part of that set and evaluate the model, the quality of generations by recall. Then we also evaluate precision, but the main study is concerning of recall. Then we examine the pre-training, the pre-training, optimization, and decoding strategy effect on recall. The second one is beam search-based sampling strategy, which avoids duplicates and maximizes recall. We implement a custom beam search with a large beam size to maximize the recall. And the last one, we construct a formula which we can use to predict the recall and precision before actually generating any molecules. So how molecules can be represented? There are many representations, binary representations, string representations, and etc. We will talk about this during this topic about binary representations and string representations. A molecular fingerprint is a unique binary representation of a molecule's chemical structure and properties. It is used to compare two molecules and to measure the similarity between two molecules. The similarity in case of binary fingerprints is calculated as Tanimoto similarity. Here is an example of a fingerprint. Each position is responsible for some structure. If there is one, it means that structure exists in that molecule. Binary representations are unique for all molecules. For a single molecule have a single unique binary representation. The next is one-dimensional representations of molecules by strings. That is a line notation. It describes chemical structures using short ASCII strings. It may not unique for a molecule, but for example, in Python, there is a library named rdekit, which gives a single unique smiles for each molecule. We will call the canonical, the unique molecule of each the unique string of each molecule canonical. So there are canonical smiles and randomized smiles. Smiles strings can be invalid, so the model can generate invalid strings. I also want to note that smiles are constructing by traversal of molecular graphs. Next is selfies. Selfies is very similar to smiles, but it is almost valid. So almost all molecules that our model generates are valid selfies. The corresponding selfies of canonical smiles we will call canonical selfies. All other versions of selfies of the same molecule we will call randomized. Next, we have chosen GDB13, which is a data set of small organic molecules up to 13 atoms. This data set contains approximately 1 billion unique structures. It is publicly available. I've set drug-like molecular subsets, and now I want to concretely define what subsets we tried to cover. We have defined 4 subsets. First one are the subset of aspirin-like molecules from the GDB13. The second one are the molecules which synthesizability score is less or equal than 3. The second one, for the second one, we have chosen 2 molecules. One is paracetamol, which we call drug-like molecule, and the second is for nitroanisole, which is a poison-like molecule. And we chose in the third subset all molecules that are closer to paracetamol and are far from for nitroanisole. And the second one we call equal distance subset. There are molecules which have equal distances from paracetamol and for nitroanisole. Initially, we have intuitions of the complexity of these subsets for the model. We thought that the modern models can easily find patterns between the molecules in these aspirin-like molecular subsets, but we thought that it will be harder to find patterns in the, for example, equal distance subset. What models we have chosen? So we have a GDB13. We extract the first subsets from GDB13. We pre-trained an OPT model, 1.3 billion OPT model on that subset of selfies, that set of selfies. And then for each subset, we fine-tune, continue learning the model using 1 million molecules from respective subset. For example, we pre-trained the model. Okay, I will tell later. What about the results? We have measured both precision and recall. This is results for precision. These are percentages. Here we have chosen a top 1 sampling strategy and generate 10 million molecules from these 4 models. We have 2 strategies for pre-training. We have trained the model by canonical selfies, and the other type of pre-training is trained on randomized selfies. I want to note that in all training sets, we have only 1 representation for each molecule. Here we can see that canonical pre-training gives the worst results for all subsets, but randomized pre-training always help the model to get better results. Except for SAS, the second subset. That subset is the easiest one for models to capture. Here we can see that the hardest subset was the fourth one. The model can't find a pattern. Here are the results for recall. It is also for 10 million generations, but it is unfair because the subsets aren't of the same size. Therefore, we have generated not for the fixed size for each subset, but for each subset we generated the number of that subset's molecules and evaluate the recall. And the dynamic is the same for the recall as was for the precision. The recall results are worse than the precision results because the sampling strategy is IID, and for generating many times, the model started to repeat the molecules which has already generated. So we have also examined the role of pre-training, sampling strategy, and loss function. Here we can see that randomized pre-training always helps the model to learn better patterns, and without pre-training, the model is performing worse. And here you can see the upper bound. If the model samples uniformly, it will have the upper bound, these upper bounds for the recall. And if we choose IID, the precision will always go up. And here's the role of our loss function. For this, we construct another training set. For each molecule, we constructed a small set of 8 representations, and the model learned. For the first line, the model chose the minimum loss and continue to learn for that representations. For the third one, the model chooses the loss from that 8 molecules, which is the maximum. And for the second one, it chooses the model chooses the mean loss of all 8 molecules, of all 8 representations of the same molecules. We can see that the second one is always better. The third one is the role of sampling strategy. We use both IIT sampling strategy and beam search. For simple autoregressive sampling, the precision is going up and the recall is going down, which we can't see in case of beam search. In case of beam search, the precision is going down and the recall is going up. So we notice that beam search is recall-oriented sampling strategy. For the last one, we formulated defined formulas which can help us to predict the recall before generating new molecules. Here M is the number of subsets of unique molecules, V is the number of validation sets molecules, and G is the number of generated strings. Here we constructed another validation set. Actually, we have chosen a validation set from to be 10,000 molecules, unique molecules, but for each molecule we iterate for 1 million times and randomize that molecule and construct a large validation set in which each molecule has multiple both randomized and canonical versions. And PEG is the probability for molecules single string representation, and this sum is the probability of the molecules to be generated. The probabilities are given by the model. Okay, that is how we can measure the recall before generation. So having a small validation set, we can calculate the probabilities on that validation set, and using the probabilities that model gives for that validation set, we can calculate recall. We can also calculate the number of unique true positive molecules, but we can notice that we need the number of subsets unique molecules for that. But for predicting recall, we don't need actually the whole number of all correct outputs in this subset. So we can also predict the precision like we do in the case of recall. We do various experiments from 1 million generation to 10 million generations, and use also different sampling strategies, top-K sampling, top-pass sampling, and use also temperature scaling, and calculate both actual results and calculate also the predictions given by our defined formulas. And the Pearson correlation is approximately 1 for 0.9997 for precision, and approximately the same for recall. So we can almost accurately predict for each subset the both recall and precision in without actually generating any molecule, and it can help to for model selection. Not that the formulas were in the were defined in the case of top-1 sampling, but we can modify them to work also for top-pass sampling, temperature scaling, and top-K sampling. Here is the graph for predictions with the actual results. Green is the prediction results for precision, and red is the predicted results. They are very similar. The next is the beam search. We have implemented a custom beam search because in order to generate with large beam sizes, we have chose from 1 million to 10 million beam sizes. Each step saving, for example, 1 million the most probable molecules. Here are the results of beam search. Green is the recall, yellow is the precision. Here we can see that as the precision is going down, the recall is going up as we sample more and more with beam search. So we have defined a benchmark for evaluating language models. We have analyzed the factors which affect the recall, and we give the path towards improving the recall through sampling methods. That's it. Thank you for your attention. If there's any question.
I have a question. Maybe I missed. Do you have any, depending on whether you train the model on smiles or selfies, is there any change in accuracy metrics? I mean, if you change the representation from, for example, smiles to selfies, do you see any increase or decrease of the accuracy metrics?
We haven't examined accuracy or recall or precision.
I mean, recall or precision.
Yeah, we haven't examined we haven't done the same experiments for the smiles. That's why I can't say anything about the comparison of smiles on surface.
Okay, no other question. Thank you very much.
Thank you for your attention.